we did before last week and what we're supposed to do today. OK, so the big goal for this class is to model uncertainty. So we are here to learn how we can model uncertainty. Because the world is uncertain, and we want kind of modeling the world. We are engineers, you know. I think so. Yes, so you want to model the probabilistic world or uncertain world. And to do that, you need to have some tools for that. So random outcomes are not easy to work, so we need to mathematically explain them. We started with axioms. We started with axioms of probability, some formal foundation to explain probability in a mathematical way. And then we moved to random variables. That was the basic random variables. But the simplest random variables that are discrete random variables, you learn how to actually define some random variables that outcomes are countable. So 1, 2, 3, 4. Later on, we can see continuous random variables that are more interesting. But still, we are in this space. What else? We also talked about general framework for random variables. We explained that as a family of random variables. We said family of random variables have some certain similar characteristics. Like, for example, they have a probability mass function, same probability mass function. That was one of them. Last week, we talked about Bernoulli random variable as the simplest random variable ever you can see in your life. Just success and failure, 2 outcomes. If the success probability is p, failure is 1 minus p. So we explained that as the simplest random variable or simplest family of random variables. So it was just one trial for Bernoulli. If we do many trials, same Bernoulli, but multiple trial, we move to another family of random variables called binomial random variable. So this is what we learned last week. Also, we talked about geometric random variable, but still, we are in that space. We want to continue this journey by expanding still this family of random variables similar to binomial, but a little more general. Like, for example, you want to model some rare events that happening, but multiple times. For example, you want to see what is the probability of clicking in actually university website that so many people can click in that, but the number of users are going to infinity, but the probability is very low. This is kind of binomial, but with some certain characteristic, because we don't know n. exact n. We don't know it. We know n is too much. N is so much. And we don't know p. We don't know probability. But we know some average. We know some average of, for example, clicking in a university website. Like we know every second, for example, there is possibility of clicking 2 people, for example, in this site. So, something like that. And this is happening a lot. Lots of other applications, too. When, for example, in LiDAR, this is happening a lot. In sensor, because LiDAR sending lots of, beams to feel the area, 3D area, to understand, to actually model the area, send like lots of beams, and some of them can miss. Some of them can be, not work properly or failed. So probability of that compared to this much sending. First of all, sometimes we even don't know how many trials we are doing. We don't know n. But we know n is too much. And probability also is very low in this case. Like, for example, in LiDAR, probability that one of the beams is failed is very low because this happened if it's happened very low anyway. So the probability is very low. N is very high. But average is given, kind of given. So today we want to study this kind of phenomenon. So a kind of binomial, but more general way, when n is going to infinity and p is going to 0. This kind of probabilities or familias of random variables called Poisson random variable. We're going to talk about Poisson random variable today. And also, if we get a chance, we might explain uniform, another simple random variable, when you have a certain time, but probability are equal. So that's what it's called uniform random variable. We're going to talk about that too, if we get a chance. Also, we're going to talk about cumulative distribution function. Another way to explain random variables is using CDF. We can see that as well. So let's get started. First of all, to move from binomial to Poisson, we need to have one example. So I imagine we have a sensor. LiDAR is a good example. LiDAR, because LiDAR sends lots of beams, and based off the time we send them and receive them, we can kind of estimate the distance or depth and get perception of the surrounding. For example, imagine we are sending 100, we are checking 100 points. So n is 100. Another thing that we know in this sensor is that the probability of failure is, we know the probability of failure is about 2%. Okay, we know this as well. First of all, I ask you, what this distribution look like? What type of distribution is that? We have probability of failure is given. So we have 2 cases, failure or success. Okay? And also we have many number of trials. What type of probability is that? What type of random variable is that? What class of random variable is that? Yes? Any idea? Binomial. Yeah, it's binomial. So binomial is a Bernoulli. This is kind of Bernoulli because it's false, true or false, or success or failure, but 100 times. So it becomes binomial. So this is binomial with, n is 100, and p is 0.02. Okay, make this. Okay, here too. Okay. Oh, sorry. So it's binomial. X is binomial. And yeah, sorry, X is binomial. And N is 100. And P is given, 0.02. Okay, another question. What requirement we need for this assumption? If this is binomial, yeah, we know N. We know P is given. What other assumption we need to have binomial? We tried N time, like the sensor sensed N points. So are they supposed to be independent? Yeah, independence is another chance. So we need to have independent trial. Okay, so that's one of the conditions. So we have two outcomes, fail or not fail. That's another condition that we have it. Constant probability that we also have that, and fixed number of trials. So that's binomial. Okay, so let's change the scenario. This time, for question 2, let's consider we are modeling number of actually times that users around the world clicking in a university website. What's the university website? www.mtu.edu, for example. So we want to see what is the number of times, like what is the probability of the random variable x is equal to k. K is the number of hit for the website of University of Michigan Tech. So we want to compute this. Is this look binomial to us? We are in binomial. We had something similar here. P of x is equal to k. That, for example, we want to see 2 times failure, for example, in that case. That was 100 k, or let k be 2, for example. In that sensor example. If the probability of success is 0.02, and 1 minus 0.02, 100 minus 2. So 100 minus 2 failure, 2 times 100 minus 2 actually success, 2 failure, and combination of 2 from 100. So that was binomial. But here is also we want to find number of hit. That was number of failure. Here is number of hit. But is there a fixed number of trial in this case? Do we have the number of trial in visiting the Michigan Tech website? We don't know. We just know that is too much. That is so much. Okay, so this is the only thing that we know. So we don't know exactly how many trial we have. So the answer is no. Okay? So actually, I want you to think about that. Maybe with your friends, think about that for a second and answer these 2 other questions. Do we know how many atoms occur? And can events happen at any real time? So these questions specify, can we model this with binomial or not? What you are thinking. Can you just talk to your friend close to you and think about that? So the idea is that we want to model this system. We want to model a number of hits, because number of hits is random. We are modeling hitting a website, university website, that is happening a lot, is around the world. So there is lots of opportunities and is infinity, can be infinity. It's very large. But probability is very low. So in this variety of experience, the probability of hitting somebody randomly come and go to a university website is low. Probability is low, but still we want to find probability of, for example, XB2, something like that. It's very similar to that. So, okay, so what do you think about the second question? Do we know how many attempts occur per minute or per second? Can we find that? Yes or no? Yes? What you're thinking? Did you talk together? What do you think? Okay. So, if this is yes, can events happen at any time? Or if it's no, it's still the same. Can this happen in any time? It means this time is continuous time. Because in binomial, we don't have anything continuous. Everything is discrete. So again, go back to this question. Can we know how many atoms occur? So when I'm asking this, it means we know, for example, can we observe when first trial happens, second trial happens, third trial happens, or users just arrive randomly? Users just arrive randomly. It's not something that we can observe. So this is something that we need to consider. This is not attempts not observable. So users just arrive randomly. Okay, so this is another thing that's happening. What about the time? Can we talk about the time that this happening is can events happen in any times? Yeah, it can be happen. this is random things, Users just arrive randomly. Users just arrive in any time. It can be in 0.1 second, can be happen in 0.0005 seconds. Like many people, and even at the same time, but the operating system gonna fix that that issue if many people, hit at the same time. In reality, that's not going to happen. So click can happen in a continuous time. So the time is continuous. OK, so the time is continuous. So OK, so that's but still, we are trying to find probability of x is equal to, for example, 2, like the before. So can we say this is kind of binomial? Yes. We can say this is kind of binomial, but the kind of binomial that n is going to infinity and p going to 0, something like that. This is a foundation for the new random variable class of random variable that called Poisson random variable. So we can explain it in this scenario. So this is actually happening when the number of users is going very high, okay? Because in reality, internet has many users, and so many people have a chance to go and open the Michigan Tech University website. So the n can be infinity. But the probability of clicking is very low. The probability is going to almost 0, okay? But the average is something possible. Now we can say the average expected value of x is, for example, 2 hits. This can happen. 2 hits per second is normal, can be happen. But in binomial, what was the expected value in binomial? Do you remember what was the expected value of binomial? NP. NP, OK? So the binomial, so NP is equal to 2. N going to infinity, P going to 0, how NP can be 2? So this is something that actually make the idea to we need another kind of family of random variables that can model this kind of phenomenon that are very rare because p is going to 0, but there is lots of opportunity to happen, and there is lots of things in nature that follow this kind of distribution. So this called Poisson distribution that we're going to talk about in next slide. Okay, so let's go see who is Poisson. Little story behind it. Poisson, this handsome, is actually he was living in France. He's a mathematician in almost 1800. And he was studying probability, and he was actually studying rare things that happening in nature. And he was actually working with the French government. And in that time, French government were dealing with lots of legal stuff. And his responsibility was to find in this legal stuff, in court and these things, sometimes some, for example, in court sometimes not all the time, but sometimes something happened that some person that is innocent going to jail. So they wanted to, but they had lots of data. In probability or in studying, statistics, we need data. And he was working in that, actually, data to figure it out how he can model that. But in that time, he was mostly working cases like he was working in convictions in court or accidents that are happening or printing errors. In that area, this was the problems that they had. But right now, we have so many higher problems that can fit in this category of random variables. Like, for example, you saw the website hit that's happening a lot in these days. Or, for example, traffic accidents. We have so many streets around the world, but the number of the number of accidents the probability is low, but possibility is a lot. Or in robotics, sensor detection, LiDARs, and these kind of detection events, that's also something that happened a lot because false alarm can happen, like random photon can go to LiDAR and detect false, this can happen. Or in radiation emission, also that happen very rare because to do that, atom need to, the probability of that is very low. So, but those things that I mentioned also, they have some certain characteristic with this Poisson. Why? Because they have very large number of opportunities. And each opportunity has very low, small probability, and events are independent. So he actually developed a new family of random variables that is with his name, called Poisson. But this Poisson has one coefficient, alpha, that we can talk about that. So he introduced his probability mass function like that. Maybe you ask me, OK, what is this coming from? We have an exponential family. We have an alpha k. And first of all, what is alpha? So alpha is an Poisson, we call it Poisson factor or Poisson rate, and is a function of time. Okay, so I should explain this lambda first in the last slide. So when in so before that, let's see how this is coming from. So probability of x is k in binomial is what? Is n k p k p minus 1, or sorry, 1 minus p, 1 minus p, n minus k. Okay, so this is binomial. So imagine we make a limit of this when n going to infinity, and also p going to 0. Okay? So limit of p of x is k. This is going to go to something like this. How we can find that? I'm not going to compute this, but this is something that is not difficult to compute. You just need to do some math, and yes, oh, where is that? And limit, you can compute that. So this is coming from that. So it's not that complex. So it's going from the limit of binomial. But what is this lambda? Lambda is the average NP in binomial. Average in binomial. That is average arrival time is a rate, so it's per unit time, for example, per second. But if we want to make it in time, for example, what is the number of hits in 5 minutes or in 60, for example, seconds, T is that interval. So T is the interval, time interval length. But still, K is the number. So anytime you want to see if this system is, for example, Poisson or not, just remember the example of hitting the website. Okay, so just remember that. Okay, so we want to model the variable, random variable x, that is the number of hits for the website. So the k is the number of hits. So, but we want to compute it in a certain time. Like, for example, we want to see what is the probability that website, university website, hit, 5 times per second. 5 times, k is 5. Second is the t. But what is the variables? What is the actually parameters for this family of random variables? Parameters are alpha. Alpha is the parameter that we have. K is given. The only parameter that we have here is alpha. In binomial, we had multiple parameters. We had P. We had, what else we had? We had N and P parameters. But here we just have alpha. Alpha coming from lambda, that the lambda is the average in binomial. Is given, average arrival rate. And T is also, they're going to give that as well. So, okay? So let's clean this and see what else we can talk about Poisson random variable. Okay, so the Poisson can model random arrival in time. So this is what we said. So applications, web requests, phone calls, for example, can model in that. Radioactive emissions, radiation, can model by that too, because they are all rare and lots of possibilities. The opportunity is a lot, but probability very low. Sensor detection error or events, that also can model within that. And packet arrival in network or false, like failure happen in packet arrival, that also can model in that. Lots of applications, especially in our job, electrical and computer engineering, this phenomenon happening a lot. So they can model, they can be used, you can use random variable, Poisson random variables for them. It's lots of information. If you know these phenomena following this distribution, you have some prior information about them. Prior information means you are one step forward than others because you know some information that people not know about it. So this is give you lots of information, and you can use them for your design, for your job that you want to do. So this is called Poisson distribution. Let's do some example. Oh, before that, let's find moments. We already talked about two moments so far, mean and variance. So we know the mean is actually, you can compute mean using probability mass function. This is the probability mass function for Poisson. So we know expected value of x is equal to sum of x, that here is k, and alpha k e minus alpha k factorial, and k going from 0 to infinity. So we know that. But here we have something interesting. Anybody knows what e power minus a means? Yes?
It's a constant, so you can pull it out of the sum.
So what?
Well, sorry, I might give it a head, but yeah.
No, yeah. So, you are saying it's a constant going out of the sum? It's not, it has, oh yeah.
Yeah, it's a constant, so you could just remove it from the sum.
Yes,
Yeah.
that's true. That's true. But it's, yeah, but my question is not that. Anybody knows what this means, like e power minus x in general? So this function is very interesting function. This function called decay function. Decay function is a function that decaying in time. Like when x is going to infinity, this is going x, for example, infinity, e minus x going to 0. When is 0, this is 1. This function, because e power 0 is 1, so this function called decay function. Remember this decay function. You're going to see that later in your life, in your career. So this decay function is another function that you're going to deal with that for modeling so many things. Because it's something that starts from 1 and going to infinity and becomes 0 eventually. Here is also interesting. But let's see how we can deal with that. OK, I need to clean this up. OK. So the mean is alpha. Why is alpha? Because this value is, this sum going to be alpha. How? Yeah, let's try that to see how easy. Because of this exponential family, this becomes so simple. OK, so we have k here and k factorial here. So k and k factorial can cancel out. This is going to be k minus 1 factorial. It's correct? Yeah, because k factorial is k multiplied k minus 1 factorial. OK, what else we can say about that? As you mentioned, we can bring a power minus alpha out. But also we can take one alpha out too, alpha and e minus alpha out. Let's see what this is going to look like. K minus 1 factorial, a k minus 1. OK, so this is something familiar too. So why? Let's do some changing, for example, k. I put k minus 1, define another variable like j. OK? that is k minus 1, like a shifting index, like shift index, okay? So this is going to be a power j factorial. J from 0 to infinity. Okay, because here was, oh, what happened? Oh, of that. Oh, there. Okay, so nothing changed here, okay, because my screen just, okay, so this is going to be this one, and is alpha. Is alpha. Any place I put A is alpha. Sorry. E minus alpha. Okay. Anybody can tell me what this sum is? Yes. Yes, exactly. So you're good in math.
No, this was on my homework last week in another class.
Oh, yeah, that's, yeah, this is actually, I think in last few sessions also we talked about that. This is e power alpha. Okay, we have e power alpha, e power minus alpha, so they cancel out and the alpha get out. So the result is alpha. So that's why it becomes so simple. So mean is just alpha. So the alpha is not a normal coefficient or parameter. It's also the mean of Poisson random variable. It's very interesting. Okay, any question about this? Let's go for variance. Let's see variance. I also claim that variance is alpha too. Okay, so how we prove this one? So first of all, we know what is alpha. Alpha is lambda t, and lambda e is the rate, like the rate of that event per second, for example, and t is a period that this happened. Like, for example, anytime you want to understand what's going on, just remember the clicking example. We have a site, we are clicking, we want to see what is the probability of clicking 2 times per minute, per 10 seconds. 10 seconds is the t. And we have some information. We know that the average of clicking is 2 per second. So we have lambda. Lambda is per second, per time unit, okay? Okay, so this, what about variance? Let's go back to our questions. We want to find the variance. Well, about the variance, we also have some prior information. We know that variance of x is equal to expected value of x squared minus expected value of x all squared. Okay, so we know that because we have e of x alpha, so e of x squared is given. That's easy. But what about this? Can we do a little trick for this? So, okay, yeah, here there is a trick that we can do. Is x minus 1 plus x minus e of x squared. Is that equal? Yeah, because this is going to be x squared minus x plus x. It's going to be this. Okay, so we can write it like that. But expected value can go in. So this is going to be equal to expected value of x minus 1 plus e of x minus e of x squared. Okay? We know this. We just don't know this. But look at that, how we compute that. We shifted 1. Here we just need to shift it 2. Same method that you can find that alpha, same method you can find these two. I'm not going to do that for you, but you do it at home. Anyway, it's going to be alpha squared this time. Here was alpha, here is going to alpha squared plus alpha minus alpha squared. Okay. So this is same as that. Instead of x, put k. Instead of k, put k minus 1. So k and k minus 1 gonna cancel out k factorial, and this k minus 1 in factorial part gonna be k minus 2 this time. And you do the same way, and in that time, instead of bringing one alpha out, bring alpha squared out. And that's going to be, again, e minus alpha, same way. But instead of j is k minus 1, it's going to be j k minus 2. Okay, similar thing. I'm not going to do that, but it's something similar. And this is happening. Alpha squared with minus alpha squared going to cancel out each other, and again going to be alpha. That's amazing. I think it's only random variable that variance and mean are all equal. It's very interesting. Maybe not only, but it's one of the limited. Okay. That's interesting. So let's see. So the mean and variance are equal. And what else we can say? And this is the unique signature of Poisson. Wow, Poisson is amazing. Look at that. Mean and variance are equal. And they are all equal to alpha. That alpha is like Poisson rate. That is very, characteristic of Poisson. Okay, any question about this? Let's do some example. First example, of course, we want to find website hit because that's a very good example for Poisson. Anytime you want to see something like that, remember website hit. Website hit going to give you lots of idea to remember what kind of random variable you are dealing with. Okay, so website hit has lots of opportunity and going to infinity. Number of users can hit are a lot, but probability is very low. Okay, but we have some average rate given. Lambda is 2 hits per second per time unit. Okay, so that's a Poisson, but it doesn't give us alpha. But we need to compute. What we want to compute? We want to find probability of no hit in 0.25 seconds. So we want to find probability of x is 0. But t is 0.25. Lambda is 2. Okay, so alpha is 2, 0.25. Okay, just need to put in a formula. So the formula was what? This. We have alpha power 0, anything power 0 is 1, and e power minus 0.5, you can compute that as well, is equal to 0.607, like 60%. So the probability of no hit in 0.25 is almost 60%. Good. It's good information. Good information. Let's do example a little more complex. What about if we want to compute probability of no more than 2 hits in 1 second? No more than 2 seconds. No more than 2 hits. So it means P of x is no more than 0 or equal to 2. Okay, what is this? Okay, so it means k can be 0, k can be 1, because it's discrete, and k can be 2. Again, what is alpha? Alpha is, t is 1, because it's 1 second. Lambda is, like before, is 2. So alpha is 2 times 1 is 2. Okay, again, is a Poisson. So another thing that we need to consider is that P of like x smaller or equal to 2, because it's disjoint or mutually exclusive, disjoint, it equal to P of 0 plus P of 1 plus P of 2, because it's mutually exclusive, because it's disjoint. This is another axiom number 3, remember? Okay, so we have that too, so we can compute that based off this formula. So we need to compute P of 0. So P of 0 is equal to, okay, let's write it here. We need to compute P of 0. We already computed P of 0, E minus, oh, no, sorry, this is different. Because the coefficient, anyway, I have the solution. I don't want to compute them all, because we need to put these values, because we have alpha, we have different k's, and we just need to put in formula to find that P of 0, P of 1, and P of 2. You can compute them, and it's going to be the result, and add them together. And this overall going to be this, 0.67, not that much difference, Okay, so this was another example of Poisson distribution website, heating. Any question? Okay. So that was about Poisson. So about Poisson, to just remember that, is kind of binomial when the number of opportunities increase to infinity, and the probability of that phenomenon is very low, or probability of that event is very low. These two characteristics, and also independent, of course, these 3 characteristics makes that random variable Poisson random variable. You always need to consider. You're going to see them a lot, especially in, sensor fusion, anything related to robotics, error detections. This kind of stuff is all Poisson. That's why we need to know Poisson very good in our career. Okay, so that was the Poisson story. Another thing that we're going to cover before finishing the class is cumulative distribution function. So we already talked about random variable. We talked about probability mass function for discrete random variables. Probability of mass function is specify the probability that this discrete random variable has a certain value x, like is equal to 2, for example. So we know that. Okay. But what about sometime we want to find probability of x is less than a number? What is this one? Like, for example, you want to find, for a sensor, probability that the sensor error is less than 2, for example. You're talking about you're not talking about one time. You're talking about an accumulative time. From infinity, from minus infinity, so what this means is from minus infinity to x. In this period of time or space, what's happening to the probability? That's called cumulative distribution. And the notation that we are using for that is capital F of x. X is a random variable. And lowercase of x is the value, okay? Okay, so let us study this a little bit. Of course, it's very simple. You just need to add them up. In discrete random variable is very easy. But let's do some examples and study this. So this gives the probability that x is no larger than x, of course, okay? And what is the relationship with probability mass function, okay? Probability, the cumulative distribution is actually sum of probability mass function in different points less than like we call it xi, for example, if xi less than x, okay? So let's see example of this. The picture, for example, this is for actually fair die, because for when you are dropping, so you have, like for example, x is 1, 2 to 6. So it's a random variable for die, okay? So it's a random variable. And probability of, for example, between 1 to 2 is 2 per 2, and when we add it with 2 to 3, it's going to be 4, and it's going to make a step function, and it's increasing. This is for discrete. For continuous form, it's going to be actually also increasing function. But this is, as you can see, this is increasing function. It's not going up and down. So this is characteristic of cumulative distribution. First of all, when we go to infinity, the cumulative distribution becomes 0. When we go to 1, it's going to be 1. Because when we add them up, it's going to be 1. That's a maximum. And it's not decreasing, so it means if x prime is bigger than x, f of x prime is also bigger than f. As you can see, this is increasing. So if x is bigger than, if x prime, for example, bigger than x, f of x prime is also bigger because it's increasing. This function called non-decreasing function. And it makes a step function or a staircase shape, as you can see in this case. And if for two values like b and a, if b is bigger than b, probability of x is between A and B is f of B minus f of A. That's the important one. Let I clean this. This is actually important one because you can find not just probability of x is less than something or bigger than that if it's be in a this actually interval between A and B. So this is also something that you can get from cumulative distribution. So the interval probability can compute it using cumulative distribution function. Okay? So it's just definition. Another way to look at the random variables. It's not complex. It's like probability mass function that we had. We also have CDF, cumulative distribution function. It still is a function, but it's a cumulative. It's adding them up from minus infinity to this moment. Because it's discrete, it's so easy. We just add them. But if it's continuous, what's going to happen? Instead of sum, we're going to have integral. That's it. We're just going to have integral if it's continuous. But here, because it's discrete, we just add them up. They're we sum them up. OK, let's do example. OK, imagine we have a actually example. We have a random variable that is a discrete random variable. We know a discrete random variable can be explained by probability mass function. And probability mass function can be explained with a chart like that. So this chart gives you all information, like saying probability of x is equal to 0 is 0.3, and probability of x is equal to 1 is 0.5, and probability of x is equal to 2 is 0.2. But what about what is probability, the cumulative distribution, CDF? We want to find CDF. Okay, we have this probability mass function, and we want to find CDF. Okay, let's do that. So what is CDF? So CDF is, we know probability of x is smaller or equal to, OK, actually we want to find, yeah, this is what we want to find. But x is also given, and x is 2. Like we want to find probability of x is smaller than 2. What is this one? P of, like f of x2. We want to find this. OK, yes, so what we need to do, first we need to find for x less than 0, what is P of, f of x for x less than 0. Less than 0 is 0. What is f of x if x is between 0 and 1? And 1 is P of x is 0, that is 0.3. OK, we know that. And f of x between 1 and 2. Between 1 and 2, OK. 1 and 2 is equal to P of x is 0 P of x is 1. When we add them together, 3, 5, 8. And for x bigger than 2, also we can find that as well. X bigger than 2 is, I'm not going to write them, but it's p equals 0 plus p equals 1 plus p equals 2. When we add them together, it's going to be 1. Okay, so if we draw that, it's going to be like this. This is x. This is f of x, cumulative distribution function. Okay, so between 0, 0, 1, 2. Or maybe I start from here. 0, 1, 2. So less than 0 is 0. Okay, let's change another color. Less than 0 is 0. Between 0 and 1 is 0.3. Between 1 and 2 is 0.8. And between 2 to infinity is 1. So that's a step function that illustrating cumulative distributed or distribution function. Okay, that's it. Let's see. I need to clean this up. I don't need to. I can go to next page. Oh, yeah, maybe I clean this up. Here is more explanation of that. Instead of drawing with the step function, you also can show it in this, this shape. Okay, so the last part that we want to explain is uniform random variable. That's the last things that we're going to see in discrete random variables. And it's very simple. Uniform random variable is the type of random variable that has two characteristics. It has two things, k and I, are integer. So, all integer between k and l has equal likely. So, for example, anytime you want to remember uniform random variable, you can remember dice. So, for example, in dice, probability of each one, like 0, 1 to 6, is all equal. And they are all uniform. That's why it's uniform distribution. It's all equal. So, like x can be, if it's 1, 2 to 6, they are all equal. Probability of x is 1 over 6, for example. 1 over 6, something like that. It's all equal. This type of random variable called uniform random variable. Okay? So how we can compute that? So in dice, it was between 1 to 6. This interval, so k and l, are 1 and 6. But it can be anything, you know. If you want to have, for example, k and l like something else, so the probability is going to be 1 over 1 minus k plus 1. Let's see some example. Okay, before going to example, first we can talk about the mean and variance. We're going to talk about that next class. I'm just going to cover that fast because we also have uniform random variable in continuous form. So that's why we're going to talk about this next class. I'm just going to tell some example, and we can finish this class. So imagine n be the number of showing in die, fair die. So this is the uniform distribution between 1 and 6. So the probability of n is equal to each of them is equal, and n can be 1 to 6. So our outcomes are like, so this is the general example for uniform random variable. We can talk about computing expected value and variance next class. Any question? Okay, so see you next class. Do we have assignments coming?
Please start.
Do you have any exams coming up?
I'm really on the
Do you have an assignment?
This guy. I have no
good. I'm too.
We made a skip.
Do we have design fundamentals?
We
Do we have design fundamentals?
Design funds?